Hello everybody. In this class we shall discuss certain performance issues which are having some common element for both ADC and DAC, and this is in the form of offset error, gain error, differential and integral nonlinearity error. So, these are the terms that we shall get familiarized with, and we shall see how it matters for ADC and DAC operation. And also we shall look at one IC, analog to digital converter IC 0804, okay, and how it is used. So, that also we shall see in this particular lecture. Now, when you talk about performance issues, and we have been discussing ADC in last two classes. So, we had seen that ADC is a closed loop system. Okay. So, it has got both analog components and digital components, isn't it? So, the error will be contributed by both of them, and the digital error, the part is mostly comes from the what is known as quantization. Okay. So, how many bits, how many discrete levels that you are having, that is actually giving you some error right in the beginning. If the number of bits are more, then number of levels to which the analog voltage can be associated with, okay, are more. So, the in between steps are where the ambiguity could be there. Okay. So, that is less. Okay. So, this is certain thing which is coming from the digital digitalization part or digital part of the error. That is how it is visualized. Okay. And if the comparator is centered, then this particular error would be like this, depending on the input voltage from plus half LSB to minus half LSB, it will be within that particular range. And if it is the analog voltage is such that each of this value within plus and minus half LSB is equally probable, okay, then we can calculate the mean square error of 8 of this particular error. This is as Ej square dE, and all of them are equally probable. So, probability of this occurring is 1, and if you integrate, then you can see that it is q square by 12. And if the input is sine wave, okay, then the corresponding signal to noise ratio for such ADC can be calculated as 6.02 into the n, which is number of bits, okay, and this is its value. Often it is neglected, right. So, more the number of such bits, more is the signal to noise ratio. So, noise here is related to quantization error, or also it is called quantization noise. Okay. So, more of it, if you want to know, right, you can pick up any digital signal processing basic text where this part is discussed with a lot of details, right. Fine. We take this result just here to know that this is an important performance issue of a ADC, right. Is it fine? And also we take note that if we increase the number of bits, then this quantization noise or this part is effect is less, signal to noise ratio is higher, right. So, the other thing that is important here is the analog part of the error, right, and which is for which the main source is the one that is coming from the comparator, okay, the switching that is taking place, and we have seen the various things from the comparator. We are going to this counter and various other places where the actual count is happening, all right. And variation in switching is happens because of this offset, gain, linearity of the amplifier, all those things, okay, and which often depends on the input voltage, temperature, okay. So, there are some other sources. So, we shall look into them and understand them a bit more in the subsequent slides. Okay. So, we begin with offset error. Okay. So, offset error is also called zero scale error. Okay. This is also known as zero scale error. What is it? Okay. So, for DAC, as I said, this part is common when we discussed DAC performance issues. This aspect we said we will take up together with ADC, and when we discuss certain performance issues of ADC in the earlier classes regarding how fast it works, or how many bits that can be associated with cost and other things. These are certain things we didn't discuss, so we are taking them together. So let us see, for DAC it is the step value when the digital input is 0. So as I said, this is related to 0 scale error. So when the digital input is 0, okay, ideal case the analog output should be 0. So this should be over here, right. But practical case, if you find that the value is over here, okay, then there is a offset error or there is a 0 scale error for the DAC. And how we measure it? We see that this value, this is the ideal line, okay, right, because digital and analog mapping, it should follow this line. So we see for what value of the this input digital code, this value is there. So we term it in this manner. So we can see that this is about plus 1 upon 4. So that is what we see over here, right. So this is the one that we see, right, and accordingly we say that the offset error is that of 1 plus 1 upon 4 5 by 4 LSB. Is it clear? Right. So this is the way it is measured, okay, this height. Now comes the ADC offset error, right. So ADC offset error, so again you start, if it is 0, it is 0. Then if you keep increasing the analog voltage, when the first transition occurs, okay, so the first transition is occurring over here. So this is related to this offset error or 0 scale error, right. And the mid step value is somewhere here, right, and the corresponding mid scale value will be somewhere here. So if you just note the difference, okay, so this is what will give you the offset error, right, because this is following this line, right. So either you take from this to this or you take from this to this, right. So either way you will see that it is, if you just measure it, it is plus 1 into 1 upon 4, that is 5 by 4 LSB. So in this particular example, this is like this, right, and mid step is where it is your half LSB distance, that is what we understand by mid step. Is it clear? So this is one actual diagram and this is what we expect as ideal diagram, and the difference when it is at 0 and the first transition occurs, so that is the giving you the offset error. And offset error usually is compensated by doing adjustment in the beginning when you calibrate the ADC. It is also called trimming, okay. In some textbook you will see that is written as trimming. So by that process we can compensate this offset error, okay. Now next what we see is called gain error, right. So the gain error is the difference between the nominal and actual gain points on the transfer function after offset error correction. So after offset error was there, so you have corrected it by appropriate compensation, right, and then you are finding out nominal and actual gain points. So nominal gain points is basically following the transfer function, right. So this is for your this digital input code and this is the analog output code. So this is for the DAC, right. So this is where it should reach, okay. But for the full scale value, what it has gone up to this, right. So this is your actual gain point. So this difference is your gain error. So in all these examples you can see that some values have been, representative values has been shown. So here the gain is negative, so minus 1 by 1 into 1 upon 4, so minus 5 by 4 LSB is the corresponding value that you can see as the error. Okay. For ADC, so this is again the nominal gain point, but for this ADC you can see that the actual gain point has come over here, right. So, it has reached this place, right. So, this is the difference, that is the gain error, and if you calculate you can see that this is minus, for this particular example, minus 3 by 4 LSB. Okay. So, this is the gain error. Again, this can be adjusted during calibration or trimming, and after that the ADC can be put to use. Okay. So, initially we have to look at this offset error, gain error, if there is any, and then we look at how we overcome it, okay, through compensation during calibration, right. Next is differential nonlinearity error. So, this is another important thing. So, differential nonlinearity error, often it is called DNL. Okay. So, in some context it is also called differential linearity. I mean, it should follow linear thing, but it is not following. So, it is becoming nonlinear. This is the difference between an actual step width, okay, and the ideal value of 1 LSB for ADC, and for DAC the actual step height and ideal value of 1 LSB. Okay. So, here first ADC is drawn, right. So, this is the way you can see an actual ADC is working, right. So, this is the analog input voltage and this is the corresponding digital code. Okay. So, here what you see, it should have gone from this place to this place, right, then only the change should have taken place, but it has occurred earlier. Okay. So, this error is that of here what you can see minus half LSB. If you just note the difference of it, okay, difference of actual step and what 1 LSB would have given you, right. In this case, it should have been over here, but it has gone beyond that, right. So, this is plus half LSB. So, for each of these code, the code that is getting generated here, say 001 or 100, okay. So, you can have certain DNL value, right. So, this DNL is associated with the code K, right. It is given by width of K. So, this is the width that you can see minus 1 LSB, what is the actual width, divided by 1 LSB width. So, that is how for ADC this is what you can see, how DNL for kth code is defined. Is it fine? Right. Now, DNL for DAC. So, this is your DAC, right. So, this is your step height and the ideal value. So, the step height should be what 1 LSB should give you. So, this is the digital input code and this corresponding analog output for the DAC, right. So, here what you can see that the step height is from here one particular code to another. So, the value is more than what n LSB 1 LSB would have given. So, this is plus 1 upon 4, that is magnified and you can see over here, and in this case it is less than that. So, this is minus 1 by 4 in this representative diagram. Okay. And in this case, this output, whatever analog output you can see, okay, minus the previous value whatever, so that gives you the step height, okay, analog voltage for kth code and analog voltage for k minus 1 code, then minus 1 LSB, what is the ideal value, divided by 1 LSB. So, that is your kth DNL for the DAC. Is it all right? Right. And what we can see that the counter type or continuous type converters usually have better DNL characteristics compared to successive approximation type, right. And if the this DNL limit is higher, like that of say half LSB, for such a case we had earlier considered for the quantization noise, etc., okay, that it is within this plus minus half LSB. Now DNL is adding another half LSB because of this, then we have got a 1 bit loss of resolution, right, whatever we had considered for the the quantization part of it. So in this case the SNR, so 1 bit loss means basically 6.02 n if n bit are used. So 1 bit will roughly, that is 6.02 into n, so roughly 16 dB less case that is happening. So the SNR will correspondingly decrease for a DNL value of that order. Okay. So this is something we need to take note of. Okay. And from there we go to something which is called integral nonlinearity, okay, and corresponding error is called INL error, integral nonlinearity error, okay. And what is it? This is the deviation of the values on the actual transfer function from a straight line, okay. And so let us see how it is looks like. So this is the ADC, right. So this is the analog input value and the corresponding digital code, right. So this is the this ideal transition, the dotted line, and actual is the bold line, that is what you can see, right. And what you can see is the deviation occurring over here, okay. So the deviation occurring over here. So these are the different deviations, okay. And if you can measure that is happening from the actual transfer, the straight line that is happening for the actual transfer function. So these are the different values, minus half LSB, minus 1/4 LSB or so. And for DAC, so this is your ideal and this is your actual, okay. For any digital input code, any kth code, you can see what is the actual value and what is the ideal value, the difference, that is giving you INL error. This is giving you INL error, okay. These are some examples that you can see, okay. Now we have already seen DNL error. So if you add them up to a kth point from the beginning, then you get the INL error of that particular value from beginning up to that particular step, okay. So it is summation of those values, right. And so from this definition we have already seen the ideal and actual. If you subtract, you get the INL for both the cases, okay. And then there is another term called absolute accuracy or total error of an ADC, which is the maximum value of the difference between an analog value and the ideal mid-step value, the one that you have seen, the maximum of it. It includes offset gain, integral nonlinearity errors, and also quantization errors. So all those things included, what you come up with is called the total error or absolute accuracy. So these are certain important performance metric or issues that we need to take note of when we talk about ADC and DAC, okay. Other than how many bits it requires and the time requires for conversion and all, okay. So these are also issues by which one has to pick up one from the other. Now we look at one particular ADC, because we have not discussed any ADC circuit IC example in the previous classes. So we take this opportunity to introduce ourselves with ADC 0804, okay. So this ADC 0804 is popular, often you use it in the lab, okay. So this is a 8-bit ADC, so this is 8-bit ADC, right. And this is successive approximation type. We understand what is successive approximation, isn't it? And the analog input voltage range that you see over here is 0 to plus 5 volt, okay, as such, but we shall see how we can increase, we can change it, okay. This is the input reference voltage. As it is on its own. Internally it is set by as VCC by 2, right. This is your VCC. if you want to set it to a different value, we shall see how it can be set. Output is TTL and CMOS compatible. Okay. Frequency of the internal clock is given by this formula, and R and C you can if you put in this manner 10 kilo ohm 150 picofarad, these are some standard value. So, the F is 607 kilohertz, right. Conversion time is roughly 100 microsecond, and total error maximum that we have just discussed is plus minus 1 LSB. Okay. And so, that is if you are talking about this 5 volt reference and all. So, in terms of voltage, so this error becomes 19.53 millivolt or so, plus minus 19.53 millivolt error. So, output is tri-stated. Okay. And if this output is all 0, so you get 0 volt, if all 1, you get 5 volt. Okay. Right. Now, what we discuss is the span adjustment. Okay. So, what is it? So, let us see. So, in this case, here earlier it was 2.5 volt, right. V reference was 2.5 volt, and the input voltage that was getting analog input voltage that was getting converted to digital equivalent was 0 to 5 volt, right. Now, if you make this V reference 1 volt, okay, then the full scale becomes 2 volt and the smaller value, the lowest value remains 0 volt. So, the span which was 0 to 5 volt now becomes 0 to 2 volt. Okay. So, all 1 is now 2 volt. Earlier all 1 was 5 volt, now all 1 will be 2 volt. Okay. So, this is useful, so that you can utilize the entire range. So, all the bits to encode an analog signal which is having a lower range, right. Otherwise, it will use lesser number of bits. Okay. So, accordingly the quantization noise will be reduced, okay, if you use the full range of all the bits that is available. Okay. And to get that particular reference voltage, of course, you can use the resistor divider circuit, something like this, right, and generate a reference voltage which is 1 volt DC. Okay. And if you do that, you will get 0 to 2 volt. So, in this case, the 1 LSB is equivalent to what? So, 2 volt is the entire range, right. So, 2 volt by 2 to the power 8, so 7.8 millivolt, okay, which is a better proposition. If you had stuck to this one, then your this value you had seen, it is around 19 millivolt or so, the resolution would have been watts. Okay. Fine. So, we look at other aspect of it. So, if you want to have a 0 shift, okay. So, what is it? So, in this case, so let us look at one such configuration, right. So, here this is your this analog input, right. Now, this is connected to 1.5 volt, right. V reference is 1.25 volt. So, V reference is 1.25 volt means the span is twice of that. So, 2.5 volt is this span, right. So, this is 2.5 volt, right. So, this V I minus the voltage you have connected as 1.5 volt. So, this 1.5 volt and this span is 2.5 volt. So, the lower range is 1.25 volt. So, 1.25 plus 1.5 plus 2.5, right. So, that is 4 volt. So, analog input, okay, now is going up to 4 volt. Okay. So, that is the range 1.5 volt to 4 volt that you can do through this particular arrangement. Okay. So, the 0 shift means earlier it was the lowest value was 0, right. So, if it is 0, then it will do with this kind of reference voltage 0 to 2.5 volt. Okay. With this arrangement, now it will convert from 1.5 to 4 volt. Okay. So, LSB equivalent, since the span is 2.5 volt, so 2.5 by 2 to the power 8, so 9.77 millivolt is the LSB equivalent or the resolution that you can get. Fine. And can we use bipolar input? So, earlier we had seen all the inputs in earlier examples from 0 to some other value or 1.5 to some other higher value, the positive value. So, here is an example where we see that how we can use a bipolar input. Okay. So, the Vi in this case is minus 5 volt to plus 5 volt, right, minus 5 volt to plus 5 volt, right. So, this is your Vi. Okay. And we connect a circuit like this, a plus 5 volt DC supply and a resistance network like this. Okay. So, in this case, through this resistance divider network and all, so if you calculate, you can see this Vi plus, when Vi changes from minus 5 volt to plus 5 volt, this Vi plus changes from 0 volt to 5 volt. Okay. Right. And then we are in the business. This span is this is 2.5 volt. So, this whole span 5 volt that we get. So, this is your span of 5 volt. Okay. And so, this is your minus 5 volt will be your 00 H and plus 5 volt will be your all 1 FF in hex. H means hex, right. Now, if you look at it from this Vi point of view, right, then entire range is 10 volt, right. So, 10 volt by 2 to the power 8. So, 39.01 millivolt is the 1 LSB equivalent or the resolution that you get for this particular circuit. Is it okay? Right. So, these are certain important aspects. So, other things that are associated with this ADC operation that you can start by pressing this switch and all, and there are these interrupt and various other inputs are there when you are using it with a microprocessor or other circuits. So, you can make use of them, but basic ADC operation, the functioning, the conversion of analog to digital. So, that we have just discussed. These are other control inputs, as and when you use it, you find out from the data sheet and make use of them. Okay. So, with this we conclude, and what we have seen that in ADC the source of error comes from both the digital and analog part. Digital part error is related to quantization, and in ADC offset error is found by giving 0 to analog input and increasing it till first transition occurs. For DAC, it is the output when digital code is 0. Okay. The gain error is the difference between the nominal and actual gain points, and we have seen it how it is calculated for both ADC and DAC. DNL error we have seen is the difference between actual step width for an ADC and step height for a DAC and the ideal value for 1 LSB. Okay. INL error also we have seen, and this is the deviation of the values on the actual transfer function from a straight line. Okay. The ideal transfer function. So, that also we have noted. And finally, we have seen how ADC 0804 is works, and how we can use it for different kind of operation by using span adjustment, zero shift, even for bipolar signal analog to digital conversion. Okay. So, all these things we have seen. Okay. Thank you.